Hi, everybody. I was going to do a handwritten homework 8 solution, but as I started going through it, I decided there were a lot of things that I wanted to talk to you about and really wanted to make sure you understood. So I decided to do this as a video. Hopefully it'll help you really grasp a few of these ideas. The moment of inertia stuff from chapter 11, not too hard, but when we get to doing orbital energies, that does get hard for a couple of reasons, which we'll discuss. Some of it's because of Wiley, some of it's wording of the problems. But if you can do these, you'll totally understand orbits and energies of rotation, which is the whole point of doing homework, right? Hard problems help you learn. With that being said, I'm going to start with the chapter 11 problems. They're not too bad. Recall that really, from the quiz, really what we're going to have is that angular momentum is I omega. And if angular momentum is conserved, if there's no torque acting on the system, then the initial moment of inertia of the system is equal times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. For this problem, we're told we have two disks, okay? And they are both initially rotating clockwise, which are counterclockwise, which is a positive rotation. So they both initially have positive omegas. They have different I's, and then they're going to come together, just like in the quiz problem. So our I initial, omega initial is really the whole thing. We have to assume that they're both turning and take the products of their moment of inertia and angular velocity, add them together. Set that equal to this final, and we'll talk about the final in a minute. But first I want to talk about this. So we're told that this is, for one of the disks, is 2.98 kilogram meters squared and 234. And that 234 is in revs per minute, but our answer is asked for in revs per minute. We don't need to change it for this problem. The next problem we will. 7.10 and 938. Okay. So once we add all that, we want to find omega final. And omega final will be I initial, omega initial over I final. But our I final is the moment of inertia when both of the disks come together. So that's just I1 plus I2, which is 2.98 plus 7.10. Okay, so omega final is I initial, omega initial over I final. And this was I1, omega 1 initial plus I2, omega 2 initial over I1 plus I2. If I put this in my calculator, I multiply 2.98 times 234 plus 7.10 times 938, divide the whole thing by 2.98 plus 7.10, and I see that I get 7299. Okay, rev per second is our unit circle. Now, for part B, we're assuming that instead of turning counterclockwise, the second disk was turning clockwise or in the negative direction. So what's going to happen is omega 2 initial is going to now be negative 938 rev per minute. And if I put that in, so I multiply 2.98 times 234 minus 7.1 times 938 over 2.98 plus 7.1, I get negative 938, or I get negative 591.5. So omega final is now negative 591.5 rev per minute, okay? Because it's negative, we know that that's turning clockwise, right? That's it. That's all there is to this problem. It's essentially the quiz problem. There's a little bit of units in there that you don't even have to mess with, and making sure that you understand clockwise and counterclockwise rotations are negative and positive respectively, okay? All right. Our next problem is a man standing on a merry-go-round. So a merry-go-round is basically a disc that can rotate, and this guy's standing at the center, and he's holding a brick in each hand. Okay, I guess I should make him stand at the center. And it's rotating with positive omega, or looking down from above counterclockwise. Again, his initial moment of inertia times his initial angular velocity is equal to his final moment of inertia times his final. We're told that the initial moment of inertia that he has is 5.43 kilogram meters squared, and that his final is 2.45 kilogram meters squared. And we're told that it's got an angular speed of 0.55 initially, so 0.550 rev per second. Now, one revolution is 2 pi rads. It goes around 2 pi, right? So 2 pi rad per rev means that we get 2 pi times 0.55 is 3.46 rad per second. You have to turn it into rads per second because the number that Wiley's asking you for has units of rads per second. They want rads per second. So the rest of this is pretty easy here. Omega final is just I initial over I initial, omega initial over I final. And that's pretty easy. 5.43 times 3.46 over 2.45. You can see that that's going to be 7.66 rad per second. Now they want to know what the ratio of his kinetic energy changing is. Kinetic energy of rotation is I omega squared over 2. And they're asking us for the ratio of the new over the old. So the final over the initial. I final, omega final squared over 2 over I initial, omega initial squared over 2, which is equal to, the 2's cancel away. So this would be 2.45 times 7.66 squared over 5.43, and then what did we get? 3.46 squared. And when you do that on your calculator, let's do it just to make sure. 2.45 times 7.66 times 7.66 divided by 5.43 times 3.46 times 3.46, and I get 2.21. I don't know why they're getting 2.216. I'm getting 2.214, rounding issues, but that's the ratio. It's a pure number, no units, and you should be all good. That's pretty easy to understand. Our final problem is actually for the moment of inertia stuff, is a rotational inertia of a collapsing spinning star changes to half its value. What is the rotation, or what is the ratio of the new kinetic energy to the initial? So kinetic energy final over kinetic energy initial has to be equal to I final omega final squared over I initial omega initial squared, right? Divided by 2, but they'll cancel. So first of all, I know that I initial or I final is equal to half of I initial. Okay. I can find now from I initial, omega initial is I final, omega final. I can find omega final as I initial, omega initial over I final. But remember, this is I initial to the half, right? So I initial to the half, which means that omega final is 2 times omega initial. All right, so let's put that stuff in. So this I final, remember, is I initial over 2. I'm going to leave off the 2's. 2 omega initial squared over I initial times omega initial squared. Omega initial squared is canceled, I initial over I initial cancels, and I get 4 over 2 or 2, which is exactly what we got. So really quick problem, just to make sure that you understand how to do this kind of stuff and give you a little practice of kind of generic symbolic notation in physics. It's always good to know how to do that without actually plugging numbers in, finding information. And that's it. So for the whole angular momentum stuff, really what I wanted you to know about was conservation of angular momentum. And that just means that the moment of inertia of the whole system initially times the initial angular velocities are equal to the final moment of inertia times the final angular velocities. And the system can have more than one object with more than one moment of inertia. That's the whole point of these 3 problems, just making sure you know that. Conservation of angular momentum is really something you keep in your back pocket. You have it if you need it. You don't generally go looking for it in problems. It's just kind of there. We use it in the gravitational problems to find essentially VA, be it aphelion and be it perihelion, Kepler's second law takes advantage of conservation of angular momentum. All right, so now we're on to our gravity problems, our Kepler's laws and universal gravity. And we're going to start with just universal gravity. There's a few things I want to talk about here real fast. Remember that this is G m over r squared, where m is whatever's causing the gravity. G is 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. That doesn't look like an m. Okay, that you just need to know. This, however, is equal to ma. And so these m's cancel, and you get a is G big M over r squared. Big M is always whatever you are rotating around, okay? But keep that in mind, right? So if I said A times R, and we're going to use that later, is equal to GM over R squared times R, which means A times R is equal to GM over R. We're going to use this later as well. That's something I forgot to talk about with you. It makes some problems easier because of energy. But for now, the only thing I want you to know for this problem is the force is GMM, or is GM1, M2 over the distance separating them. And what you're told is that there is a force of 3.7 times 10 to the minus 12 newtons between them, and that mass 1 and mass 2 are respectively 9.6 kilograms and 5.5 kilograms. Also, this is going to seem really easy. In a couple problems, you're going to be like, I don't know what I'm doing anymore. So this is going to go from super easy to, oh my God, what is going on? And yeah, that's kind of the point. So R squared is G M1 M2 over F, or taking the square root, I get that it's always assume the root's going to be positive. And I need to make sure that you understand a few things, which is also why I wanted to do this. 9.6, about scientific notation if you're struggling with it. First of all, look at your scientific numbers. 10 to the minus 11 minus 10 to the minus 12. This whole number is going to be times 10. So R is going to be 6.67 times 9.6 times 5.5 all over 3.7 times 10. Because when they're in the denominator, you subtract them. So minus 11 minus a minus 12 gives us a 10 to the 1, which is 10, right? So just bear that in mind when you put it in your calculator. What I do is I do them separately. So I do 6.67 times 9.6 times 5.5 divided by 3.7, multiply that by 10, and then take the square root of your answer. And it's no surprise I get 30.85, exactly what they got. Okay, this is a really simple problem, just making sure you know the definition of Newton's universal gravity and how to find it if you're given a couple things, right? All right, so miniature black holes. And now let's look at this. You're assumed to be standing on Earth, and a miniature black hole is a really massive body that's going to come in here, and it's going to pull you up with an acceleration equal to g of 9.83 meters per second squared. Okay, so we need to figure out how far away it would have to be for that to be true. And we know the force, ma, is equal to g m over r squared. This is your mass, so this is the mass of the black hole. We're told the mass of the black hole is 1 times 10 to the 11th kilograms, okay? We want to know when A is equal to 9.83, what is R? So we get R is square root of gm over A, just to be safe. They call it G, but we're going to call it, well, they call it AG, which is good. So notice this is 6.67 times 10 to the minus 11 times 1 times 10 to the 11th. And again, 10 to the minus 11, you add them if they're being multiplied. So 10 to the minus 11 plus 10 to the 11th is 10 to the 0, or 1. So really, this is 6.67 divided by 9.83. I would warn you that you really should do the scientific notation before you put it into your calculator to save you time. We don't have to put these numbers in. And like on a test, you would be putting 6.67 times 10 to the minus 11 times 1 times 10 to the 11th over. Don't do that. The answer is 6.67 in the numerator. So I get 823, 0.823, or 82.4 centimeters, essentially, right? So this is just understanding, this problem is about understanding the acceleration due to the force of universal gravity. That's what I wanted you to do this problem for, okay? All right, 49. Now 49, we're on to Kepler's laws. And Kepler's laws, we did the one with the comet. We're doing another comet here. So we'll talk this through. They're saying that a comet was seen in China in 534 AD, and it was spotted again in 1954. What this tells us is the period we're assuming is the time between two successive sightings. So this would be 1954 minus 534, or 1420. 1420 years. Now, they tell us that the eccentricity is 0.981. Pretty high, but that's, comets are notorious for that. Now, in this problem, we are in the solar system, and we therefore can use t squared is a to the third. If we weren't, it would be 4 pi squared over gm times a to the third. But here, and this would be seconds and this would be meters, here we can be in Earth years and we can be in AU, okay? But we're gonna need to turn it back into meters. So we can find A as the third root of t squared, okay? And this will give us A and AU if we do this. Take the third root, and hit math on your calculator, third root of 1420 times 1420. I get 126.3355. Keep a bunch of this. AU, the conversion is 1.49 times 10 to the 11th meters per AU. So if I multiply this times 1.49, I get 1.88 times 10 to the 13th. Let's see what they get. 7 is 3, 6, 8, 11, 12, 13. Yep, I get 1.882. They get 1.889 times 10 to the 13th. I don't know why they're getting a little bit different number. So if there's an issue in Wiley Plus, something's either I've rounded too soon or I didn't round soon enough. Let me try 126 times 1.49. I get 187. So yeah, I rounded. Yeah, I don't know what they're doing. So what's hard on this is that Wiley isn't really good about telling you what to use for your numbers. I don't know what they're assuming the AU is. Let's say it's 1.5. We get 126.3355 times 1.5. I get 189.5, which is off the other way. So 126 times 1.5 is 189 exactly, which is about what they got. I don't know what they're doing rounding wise or whatever. But their number is 189 times 10 to the 11th meters. Okay, now the second thing they want us to give is the greatest distance. Now, as something orbits, right, this is RP and this is RA. And we know from Kepler's first law that these are ellipses, and therefore RA plus EA is equal to A. I'm sorry, that's not true. RA is equal to A plus EA. Okay, now we can use this to find RA. I'm sorry, yeah, the greatest distance. We just found A and we were given E. So RA is going to be this 1.89 times 10 to the 13th meters times 1 plus E, and that's 1 plus 0.981. Okay, so multiply the answer you just found, 1.89 times 1.981. And I get 3.74 times 10 to the 13th, which is exactly what they got here. I get 3.744. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, good enough. I think you all get how to use Kepler's equations for ellipses. Not too hard. We're going to do a little bit more challenging one right now. It's a little bit more challenging because we're not in our solar system. Okay. So this tells us that a satellite is in elliptical orbit, and it gives us the period, so it gives us t in seconds, 7.65 times 10 to the 4th second. Okay, and it gives us big M, what it's orbiting, what's causing the gravity that's causing its orbit is 5.43 times 10 to the 24 kilograms. And then it gives us the aphelion radius and the angular speed in rad per second. Rad per second. And it wants to know the angular speed at perihelion, okay? So it wants omega p. Something I didn't say before, we found that mvr was equal to mvr. If this is A and this is A and then this is P and this is P, that was Kepler's second law. Canceling the m's, we get that VA-RA is equal to VP-RP. But remember that omega is V over R, okay? Or better yet, V is R omega. So I get RA, omega A, RA is RP, omega P, RP. And therefore, I get that this is actually RA squared over RP squared times omega A. They gave me RA, the radius at aphelion. They gave me omega A, but they didn't give me RP. I don't know what RP is, so how do I find it? Well, I know that I have RP is equal to, I should do it this way. RA, or RP plus EA is equal to A. So it's equal to A minus EA from the ellipse diagrams. Or in terms of RA, RP plus RA is 2A. So RP is 2A minus RA. And if I can find A, I can get this equation. So T squared is equal to 4 pi squared over GM A cubed. I cannot use the version of this. I can't use T squared is equal to A cubed, where this is Earth years and this is seconds, because we're not in our solar system. Can't use that there. I want to find A. So A is the third root of T squared times G times M over 4 pi squared. Now T they gave me. So A is, keep in mind this is the third root. I'm going to do something a little weird here. 6.67, I'm doing G first. 10 to the minus 11, okay, third root. T squared is 7.65 squared times 10 to the fourth squared, and that's 10 to the eighth. When you square a power, you just add the power twice, add 2 times the power. M was 543, and this is 10 to the 24 times 10 to the 24, all over 4 pi. So all I've done is I've separated out the scientific stuff from just the numbers. This is minus 11 plus 8 is minus 3, 21. So this is 10 to the 21st. And the third root of 10 to the 21st is 10 to the 7th. That's 10 times 7 times 10 times 7 times 10 times 7 gives us 10 to the 21. So whatever I get here, I multiply by 10 to the 20, or by 10 to the 7th. Okay? So let me do this. I'm going to get the third root of 6.67 times 7.65 times 7.65 times 5.43, all divided by 4 times pi times pi. I get 3.77 times 10 to the 7th. Okay, that's my A. And if I go back here and I plug in for A, 3.77 times 10 to the 7th, right? RP is 2 times 3.77 times 10 to the 7th minus, and what was RA? 5.7 times 10 to the 7th. And therefore I get times 2 minus 5.7. I get 1.84. RP is 1.845 times 10 to the 7th meters. And now from this, omega p is RA squared. So RA is 5.7 squared times 10 to the 7th squared. Let me do this the more normal way. Times 10 to the 7th squared over 1.845 times 10 to the 7th squared, all times omega A, which they told us was 7.207 times 10 to the minus 5 rad per second. So 5.7 times 5.7 divided by 1.845 times 1.845 gives me 9.544 times 0.0007207 gives me 6.878 times 10 to the minus 4. Is that at the fourth decimal place? Yep. So that's it. What we had to do in here was we had to know that in order to find omega at perihelion, we used angular momentum, Kepler's second law, converted V to R omega, got this ratio. We were given A and RA. We had to find RP, and we found it by finding A from the period and plugging it into RP is equal to A minus RA. Math is not hard on this. What's hard is just figuring out which equation to use next over and over and over again, right? But once you do a few of these, I mean, you really don't have that many equations to choose from. So they're not too bad. The next 5 questions start getting hard, okay? There's a little bit of issues in each one of them. So in this first one, it's all about the Earth and the Sun. And we're talking about the Earth rotating around the Sun. And it's almost circular, okay? At our perihelion and at our aphelion, hang on. Answering a question from a student. So for the Earth at perihelion, remember this is the closest, 1.47 times 10 to the 8th kilometers. I hate Wiley for this, 1.52 times 10 to the 8th kilometers. Let's turn those into meters. Why? Well, we're going to be doing stuff with gravitational, 6.67 times 10 to the minus 11 newtons, meters squared over kilograms squared. So meters squared, these have to be in meters. So 1.47 times 10 to the 11th meters, and 1.52 times 10 to the 11th meters. And I have those switched, I'm sorry. This is perihelion is always the close one. Aphelion is always the farthest away. And you can see here that the Earth is almost circular, right? What they're going to ask us is to find the variation in the total energy, the potential energy, the kinetic energy, and the orbital speed when it's at perihelion and when it's at aphelion. By variation, they mean take A minus B, or better yet, say the value at A minus the value at P, okay? That's more or less what they're saying, but they want us to take the absolute value, okay? So let's go through each of these. Now the energy at any time, right, anywhere, is mv squared over 2 minus gmm over r. Now this is little m. I'm going to call this m naught, and m will be whatever we're rotating around. So this would be the mass of the Earth, this would be the mass of the Sun. And at any other point, it's also equal to this. But by conservation of energy, this is true unless something weird happens, some outside force happens. So EA is equal to EP. Therefore, if we took the energy at perihelion minus the energy at aphelion, we would always get 0. Energy conserved, okay? Okay. Sorry, people are blowing up my phone for some reason. Now, gravitational potential energy. And here's the problem that we have with doing orbits. We have to redefine gravitational potential energy as, instead of mgh, it's now this gmm over r, okay? So the change from perihelion to aphelion, or aphelion to perihelion, remember that the energy change of gravity is negative gmm over ra. The potential energy of gravity is always negative. So minus a minus, so plus gmm over rp. Now these m's are the Sun and the Earth. And the mass of the Sun is 1.99 times 10 to the 30 kilograms. The mass of the Earth depending on who you ask, is 5.97 times 10 to the 24th kilograms. That seems to work in Wiley. I don't know why, but that's what they use. I will switch between 5.94 and 5.97. But we want this change. So this is really G, M of the sun, M of the earth, times 1 over RP minus 1 over RA. And if we put those into our calculator, let me do this right here. So I have 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30th times 5.97 times 10 to the 24th times 1 over, RP was 1.47, right? 1.47 times 10 to the 11 minus 1 over 1.52 times 10 to the 11, right? When you do that, what you're going to get is you're going to get 6.67 times 1.99 times 5.97. All that's negative 11, 30 is 19, plus 24 is 43. Divided by 11 is 32. So I'm going to get 79.241 times 10 to the 32 times 1 over 1.47 minus 1 over 1.52. And I get 1.77 times 10 to the 32nd when I do this. Okay, when I put those numbers in. That's about 1.8 times 10 to the 32nd joules. Now, before we move on, the change in kinetic energy and the change in potential energy between perihelion and aphelion, they exchange because the energy has to be conserved. If it loses some potential energy going from A to P, then it gains potential energy and vice versa. So whatever the change in potential energy is, that's the change in kinetic energy. That's the answer to part C. You could find it, and how you would find it is the same way we just did. The kinetic energy, instead of being just mv squared over 2, it's also equal to gm sun m earth over 2r for each one. And therefore the change would be, it's positive, not negative, like the over 2rp. And you can see that this is just what we did before, right? But flipped. Those answers are flipped around, okay? As far as that half being in there, what happens to that half being in there? I feel like that half needs to go away. Yeah, did they do it this way? Nope, they just said that the changing kinetic energy. So, trying to remember what happens to that half, because it would look like we would get half the energy of the potential energy, but they are the same. The only difference is that they're flipped. RA and RP are changed places. Yeah, I don't know. Maybe they are half. I don't know. Weird. But anyway, the change in potential energy is equal to the change in kinetic energy. So you should get 1.8 times 10 to the 32nd joules. The last part of this problem is actually somewhat hard. But using this, we can find it. So let's try to find the kinetic energy when it's at aphelion. Okay. That would be G, M sun, M earth, and this is the earth, over 2R aphelion. we want to find V from this. The 2's cancel, the Earth's cancel, and so I get that VA is square root of G m of the sun over RA. Okay, and I can compute that right now. 6.67 for G times 1.99 for the sun. This is going to be 10 to the minus 11, 10 to the 30th, so 10 to the 19, but it's over 10 to the 11th. So this is 10 to the 19th times 10 to the minus 11. This is going to be, all these numbers are going to end up being 10 to the 8th. So we're going to get something times 10 to the 4th when we take the square root. And I'm going to divide by 1.52. Taking the square root of this answer, I get 2.955 times 10 to the 4th. Okay, that is VA. Or, and this is in meters per second. They want your answer in kilometers per second. We'll talk about what we're doing. If I divide this by 1,000, right, by 10 to the 3rd, I get 29.5. So VA is 29.55 kilometers per second. And now, what they're asking us to do, once we've done that, is they want to know what is the ratio of V, or what is the change in velocity from aphelion to perihelion, the absolute value. We have VA. From Kepler's second law, we know this is true, and therefore VP is RA over RP times VA. We put that in here, what we get is we get VA times 1 minus RA over RP. And RA over RP, remember, is 1.52 over 1.47 times 10 to the 11th or times 10 to the 8th, doesn't matter as long as they're the same. It's just a ratio. 1.52 divided by 1.47 gives me 1.03. Okay, 1.034. So this is 29.55 times 1 minus 1.034. It's going to give me a negative number, but I'm taking the absolute value. So 1 minus this answer times 29.55. The answer is 1. This is 1. Why Wiley Plus has 0.99 there? I have no clue. Every way that I've done this, I don't get 0.99. I get 1, or a little more than 1. So if you put in 1 and it tells you it's wrong, it's 0.99. But what this is saying is VP is 1.034 times VA. So the speed at perihelion is about 30.55. It's essentially 1 kilometer per second faster when it's near the sun. And I want you to always remember that. Objects, as they orbit, closer, faster. Further away, slower. So it's kind of like throwing an object up against gravity, right? You know, at the top it slows down and then it speeds back up as it gets closer to the surface of the Earth. Same thing happens in an orbit. As it gets closer, it speeds up, slows down, speeds up, slows down, speeds up, slows down, okay? Essentially what orbits are one way to see it, is imagine that you threw a ball fast enough and far enough that it never hit the ground and it just went around and around and around, right? If you could throw it fast enough that that projectile motion curve matched the curvature of the Earth, the object would never come down. So orbits are like falling around an object that you're rotating around in a weird way. And if you do it at the right speed, you'll get circular, but otherwise you tend to get these weird ellipses, right? Because you're going a little bit further away and then swinging back in. Anyway, that's beside the point. I don't think this one's too hard. The next two get a little weird and wonky because of Wiley. Okay. So this first one is really, really, really messy. Okay. We need to find out. They want to know the magnitude of the acceleration due to rotation around these different objects. One's a planet, one's the star, one's the galactic center, and they want them in terms of g, okay? So first of all, remember that a rad is v squared over r. We're assuming circular orbits, and circular orbits means that you're doing 2 pi r, the circumference, over the period. Therefore, if I square this, a rad, which is really my quote-unquote g, is this squared, so 4 pi squared over rt, or 4 pi squared r over t squared. Now, we want it in terms of g though, so we need to divide by 9.8 on both sides. Okay, 9.80. And that'll give us whatever this number is in units of g. It says it has no units, it has units of g. So if you ever hear someone say 4g, what they mean is 4 times 9.8. Or if they say that, like in a crash, the collision, there were forces up to 10 g's, that's 10 times 9.8, or 98 newtons of force on you, right? On and on and on. So that's what this will give us. This will give us some number g's, right? But this is all we really need to care about. So for each one of these, we need to put in 4 pi squared r over 9.8 times t squared. And the only hard thing here, I'm going to move on from this. The only hard thing here is that when you plug in t, it better be in seconds. So remember that the conversion of pi times 10 to the 7th seconds in a year, t always has to be in seconds. There are 86,400 seconds in a day, and there are, well, I think the second one. So the first one, it says, if you're orbiting around a planet with a period of 1.9 days, you would do 1.9 times 86,400 and plug that in, square it. It gives you r at the end of the problem here. Tells you this is 8.2 times 10 to the 6 meters. Don't forget the 9.8. For the next one, it gives you a different radius and a different time in years. This isn't real hard, actually. This isn't the wonky one. The wonky one's the next two, 61 and 39. Okay, this is probably the worst question on this homework because it's poorly worded and it's a hard question to understand. So instead of trying to understand what they're saying, let's first try to understand something else. If we're on the surface of the Earth, right, with some energy, and then we want to get up to some energy, here we are at radius of the Earth, and here we are at the radius of the Earth plus some height, okay, that I'm going to call little h. So this is h. Just like when we did energy before, we can just write down the energy at each of these in terms of potential and kinetic. So we have gm of the Earth, mass of the object, over. Here is our Earth. I'll actually do it beside them. Times 2. This is the kinetic energy term. The potential energy term is always minus g, mass of the Earth, mass of the object, over, not 2, over re plus h. Okay, that's just because kinetic energy is gmm over r times 2 minus gmm over r is the potential energy, and that's the energy at any point. So here is gm Earth m over re minus, with a 2, minus gm Earth m over re. Okay, and we should set the energies equal to each other. But there's a small problem here, right? So what they're asking us to do is find the height where the kinetic energy required to lift sorry, the potential energy required to lift it would be equal to the kinetic energy. Okay, and that's, I mean, really we could try and do it this way, but what they say there is they want to know when the change of potential energy is equal to the change in kinetic energy, okay? And so, what we're assuming, and that they're not telling you, which is really super annoying, is that in this particular problem, we're assuming that we start off at rest and then we get to some kinetic energy. So the potential energy change is going to be negative G m Earth. Remember that the change in potential energy has to be the final minus the initial. So plus G m Earth m over r Earth. And that's equal to negative, because we have to put energy in to make it go fast, right? And we started off with 0 here. So 0 if you want. So this is what we get, right? Except that doesn't quite work by the way that they're talking about. And the reason why it doesn't work is we're going to need to have that term, this term has to be negative. Okay, so what we really want is that the negative potential energy. So what we're saying is that delta KE plus delta PE is 0, and therefore delta KE is equal to negative PE. That's really what they're trying to get at here. That's what they're trying to give you. So what I get is I get GM Earth, M of the object, over R Earth with a R Earth plus H, okay, minus GM Earth, M over R Earth is equal to minus GM E M over 2RE plus H. And now they want us to find H. So they want us to solve this for H, okay? If I move this over and I move this over, what I get is I get G, before I do that, I can see here that I have GMEM in all of them. So I'm gonna get rid of all those, and then I'm gonna move this over. So I get 1 over RE plus H plus 1 over 2 times RE plus H, okay, is equal to 1 over RE. Now, this is 3/2 times 1 over RE plus H is equal to 1 over RE. If I multiply this through, I get 3/2 RE is equal to RE plus H, or H is equal to RE times 3/2 minus 1, which is RE to the half the radius of the Earth. The Earth is 600 or 6,380 kilometers. Half of that is 190? So I guess, I don't know what they're using. They're using 3185 times 2. They're using 6370 instead of 6380. Okay, so half of this, and if this is a 7, that's not what I want. I don't know what my computer's doing right now, besides being a jerk. Okay, so 6370 divided by 2 gives us that. All right, so now we know that the potential energy and the kinetic energy, when they're equal, that happens at a height of half the radius of the Earth above the Earth. So it happens at a distance of 3/2 times the radius of the Earth. Now, as we go higher, look back at this, the change in potential energy sorry, the change in potential energy minus the change, and the change in kinetic energy. Which one of these is going to get bigger if we keep going? If we start adding to H, right? This guy is going to be less because there's a 2 here, right? So anything that we add for H, if we add 1 meter, we get 2 meters. Here, H is only going to be 1 meter. So we're actually, it's going to require us to have more energy for lifting. Lifting is the change in potential energy. I think that's what they mean. Versus the kinetic energy, they're saying, which is, as you increase beyond H, which is more the amount you need for potential energy change or the amount you need for kinetic energy change. It turns out it's the amount you need for lifting or changing the potential energy. Okay, that's annoying, I know, I'm sorry. Which brings us to, that was 61, right? Yep. Which brings us to the interactive exercise. This I'll let you guys do. You can play around with these. They're not too hard. When we look at this, if it will open, it gives us the mass, the radius, VI, all that good stuff. I don't know why mine's not opening for whatever reason. Okay, so this cool little thing, right? If we give it some initial speed, we can see where it turns back. That's what this turning point is showing us. It only gets to there. So if we want it to get gone, right, where it's never coming back, you can see that the initial speed needs to be whatever, 653 or whatever. I think you can actually put in escape speed is at the point where mv squared over 2 minus gmm over r is equal to 0, right? So mv squared over 2 is equal to gmm over r. The m's cancel, and v is 2gm over r. The escape speed from a planet. You could plug that in. Let me do that really fast. 2 times 6.67 times 4 times 10 to the 9th over 10 to the 5th is 10 to the 4th. So if I take the square root of this, I get times 10 to the 2nd, I get 730. Not too hard. The second question is, suppose the probe is given an initial speed equal to half its escape speed. What is the maximum distance it could reach? How we do that is we figure out the energy the way I just did. So mv squared over 2 minus gmm over r is equal to mv, let's say this is initial, and this is final, this is initial, over 2 minus gmm over r final. The problem is this r initial is actually the given surface of the planet, okay? Because we're starting at the surface of the planet. This is half of 730, okay? V final is 0, okay? The furthest point away it reaches is when V final is 0. So we want to find R final, and therefore R final is equal to gmm with a negative over mv naught squared over 2 minus gmm over R initial. And you could find that, turns out it's 1.33 E5. Notice that the m's all cancel, so really you have this gm, right? Okay, and if I divide through by gm, what I really get is I get minus 1 over v naught squared over 2gm minus 1 over r naught, okay? And this should end up being a positive number. Let's look at their solution real fast. Make sure I did it right. Yeah. Why did I? So I got GMM. Yeah, that part's. Oh, they This is our final. So yeah, they multiplied through by a negative sign. Um, sorry, I guess I should really do this. They multiplied through by a negative sign here, which is just this answer if you multiply through by a negative sign. And then they canceled factors of m, and then they did this, and that gave them this. They divided through by r, 1 over r, to get an easier answer here. So there'd be an r, and this would be 1 over r. If I multiply through by 1 over r, I get an r there, and I get 1 here, right? So once you do that, you can find this answer, and they do some stuff, but this is the answer right here. You just have to compute it, which is not too hard, actually. Okay, so what is the system of mechanical energy in megajoules if the initial speed equals 1/2 the escape speed? The probe mass is m times 200. And so all you have to do is find this, or find this, right? That's all. And that's not hard to do. They give you the mass, they give you the initial speed. You know G is 6.67. They gave you the mass of the planet, they gave you the radius of the planet. Figure out what those are. Mega means 10 to the 6th. So that's answer going to be in 10 to the 6th. It's negative because it has negative potential energy due to gravity that you have to get rid of. You have to put work in to escape gravity. All good. Final question. All right. This question's a bit weird, and really, the only thing you really need to know is let's talk this through and see if we can figure out what the problem is here. We want the escape speed on an asteroid with a radius of 257 times 10 to the 3rd meters. And the gravitational acceleration on the surface, g on r, is 0.309 meters per second squared. Now, we want the escape speed. And what we know is that this is 2gm over r. And we don't have m. And we have r, but we don't have m. So hold on, let's do something a little bit more creative here. So MA, we know, is GM m over r squared at the surface. These m's cancel. If I multiply both sides by r, I get that this is GM over r. So this term right here is actually AR at the surface. So V, escape, okay, is 2 times the acceleration at the surface times the radius at the surface. That I can plug in. 0.309 times, remember, meters, 2 times 0.309 times 257,000. Take the square root of your answer, and you get 398.5. Pretty cool. So now that you know that, the rest of this is pretty easy. That's one little tricky thing. So how far from the surface will the particle go if it leaves with a radial speed of 272? So mv squared over 2 minus gm m over r is equal to mv squared over 2 minus gm m over r final. Final is 0. R initial is that, and again, we're finding R final. Given V, little m's cancel. And what is big M here? Okay. If I divide through by G over M, if I divide through actually by GM over R, knowing that that is AR, okay? So divide through by 1 over AR. I get V squared over 2AR. This is minus 1, right? is equal to minus 1 over, r at the surface over r final. Okay, this is our surface. So therefore, let's multiply through by 1. This becomes 1 minus v squared over 2a r of the surface is equal to r of the surface over r final, or r final is r of the surface, 1 minus v squared over 2a r. Right, can do that. Let's make sure that that's the solution that they show. So how far they're saying that's dope. They want to know how far from the surface. So yeah, I knew I messed that up a little bit. Let's do this again. M v squared over 2 minus gm m r the surface is equal to m v final squared over 2. This is v on the surface. Minus gm m r the surface plus h. So h is how far above the surface it gets. Highest it goes at the highest point, v final is 0. So again, we can divide through by m's, all the m's cancel, and we can divide through by a, r the surface is equal to gm over r the surface. So if I divide that, and furthermore, I'm going to multiply by 1, so I'm going to get by -1. I'm going to get gm over r the surface divided by gm over r the surface, which is ar, minus v squared over 2 times 2 gm over r the surface is equal to minus gm over, oh, but I multiplied through by a minus sign, right? Rs plus h, 1 over gm over rs. So seeing this stuff cancels. I get 1 minus v on the surface squared over 2a r on the surface is equal to r of the surface, rs plus h. And again, if I want to do this math out, r surface plus h is equal to r of the surface, 1 minus v squared over 2a r of the surface. Subtract out from both sides. Minus, I don't want, minus r of the surface, okay? Which is essentially what they got here. They did some fancy algebra by multiplying through by 2ar surface and got this, and they got their height. The last thing that I want to leave you with is problem, or part C of this problem. So with what speed will an object hit the asteroid if it's dropped, assumingly from rest, 100 or 1,116 kilometers above the surface? Now, here's the thing. You've learned a lot this semester, and you might be assuming, oh, I know this one. If h is 1116 times 10 to the third meters, I can figure out how fast it's going to fall just by my v final squared minus v initial squared is equal to 2a times change of y, or height. Why can't you do that? Well, the reason you can't do that is we're now assuming that g can change, or a can change, right? And therefore you'd have to integrate this up and figure that out. But we don't have to, because it turns out we can just write the energy. Gm, sorry, I was right the first time. V initial squared over 2 minus Gm m r plus h, where this is r of the surface, and this is mv final squared over 2 minus Gm m over r. Setting these equal, assuming this is 0, I get that mv final squared over 2 is equal to gmm over r minus gmm r plus h. You can come in. I'm not recording. I'm recording, but I'm not on camera. So therefore, when I do this, I again get v final squared over 2 is equal to g m over r of the surface plus gm, sorry, minus gm r plus h. If I plug in a is gm over r, ar is that, this becomes ar of the surface, and this one I would have to multiply through, dividing by gm over r, which is ar. We're just dividing by gm over r. So r squared over r plus h, or rs plus h. And so putting that on a new slide, v final squared over 2 is equal to gm over r the surface minus gm over r the surface plus h. And now I'm using the fact that a times r the surface is gm over r the surface, right? Or actually what I'm doing is I'm going to multiply through by 1 over gm over r to the surface. So v squared over 2 a r to the surface is equal to, and since this is the same, 1 minus r to the surface over r to the surface plus h. You could leave this as g m r to the surface, but it's ar squared. Now, that means that v is 2a r to the surface times 1 minus r to the surface plus h. Plug in your values, let's see what we get. So 2 times, well, let me do the parentheses first. R the surface was 257,000 divided by 257,000 plus 11,16,000. Okay, 1 minus that number, and then multiply that by 2 times a was 0.309 times r the surface was 257,000, and then take the square root of that answer, and I get 359.300, exactly what they got. I get 30033. No, I get 3398. They get 976. Okay, so the takeaway here is that you cannot assume that g is constant, so you can't use the constant accel. That's where we started this whole course from, was constant acceleration. This doesn't work. You have to use energy of gravity, and you have to use this new term for the potential energy of gravity. And then, because of this problem being what it is, you can substitute in for gm over r ars, okay? But yeah, tough homework. Hopefully it taught you a lot about orbits and orbital energy. Yeah, anyway, good luck. Hope you enjoyed it.